Welcome back to the classes of network theory. We have already attended a class on series RL circuit. Today I will be discussing about parallel RL circuit, and we will also see the expressions of instantaneous voltage and current, how to derive them, what is the phase difference between them, and we will also simplify numericals based on the knowledge that we will be gaining today. So without wasting time, let's start the class. Now in this diagram, as you can see here, we have parallel branch of resistor and inductor, and with that parallel branch we have connected an AC voltage source which is sinusoidal in nature. Now this AC voltage is energizing the circuit, and let's say that this AC voltage source is supplying a current which is again AC or alternating in nature, and that will be again sinusoidal. Now the instantaneous voltage which is applied across this parallel RL circuit, since this is sinusoidal in nature, that expression is small v is equal to Vm sin omega t, where we already know that this small v is the representation of instantaneous value. Here it is instantaneous voltage, and V suffix m is the maximum or peak value of that voltage. Now next we will find out that the current that this voltage source supplied, since it is a parallel branch, so here the current will be divided into two parts, and let's assume that the current which is flowing through the resistor, that is IR, and the current which is flowing through the inductor, that is IL, and this small I suffix r and small I suffix l, they are the representation of instantaneous value of the currents. Now let's find out the instantaneous current which flows through the resistor. Now this IR will be simply the V by R, the instantaneous value of the applied voltage divided by the resistance of the resistor. Now it will be Vm sin omega t divided by R. And now if we want to obtain the instantaneous current through the inductor, that will be IL, and we know that in case of inductor, the voltage which is dropped across the inductor is equal to L di dt. It is the rate of change of the current that flows through the inductor multiplied by the inductance of the inductor. Now from this relationship, if we want to express current in terms of voltage, then that expression will be 1 by L integration of V dt. Now in place of this small v instantaneous value, if we replace this instantaneous value by this expression, it will look like this. Now if we follow the rule of integration, then finally after integration we will be getting minus Vm divided by omega L cos omega t. Now since the voltage, instantaneous voltage, we took as a reference because here the voltage is the common parameter between this resistive and inductive branch. So since this is sinusoidal in nature and the phase value of that voltage was taken as 0 degree, so here this cos, the current which flows through the inductor, that till now we have expressed in terms of cosinusoidal signal or wave. So we have to express that current value again in sinusoidal form. So if this cos omega t we transform into sinusoidal wave or sine, then it will be sine 90 degree minus omega t. Now since in our expression it was plus omega t, so if we want to make this minus omega t into plus, then already we have a negative sign outside of this whole expression. So we know that sine of minus theta is equal to minus sine theta. So on the other side, we can say that minus sine theta will be equal to sine of minus theta. So it is minus then sine theta. This is constant, but minus sine 90 degree minus omega t can be written as Bm by omega L, which is constant, then sine omega t minus 90 degree. So this is the current value, instantaneous current value through the inductor, and now finally it has been expressed in terms of sine. Now next we will obtain the total current or the instantaneous value of the total current in that parallel RL branch. So it will be simply the algebraic sum of both the currents. So here we will be taking the vector sum of these two quantities, so IR plus IL. Now the values, individual values of IR and IL we have already obtained, and this is Vm sin omega t divided by R plus Vm divided by omega L sin omega t minus 90 degree. So next what we will do, we will expand this sin A minus V, and we will be getting this expression. So Vm by omega L is the constant, so sin A minus B will be sin A cos B minus cos A sin B. So it will be sin omega t cos 90 degree minus cos omega t sin 90 degree. Now we know that cos 90 degree is equal to 0, so this expression altogether will be 0, and sin 90 degree is 1, so this expression will be modified into Vm by omega L cos omega t, and with that there is a negative sign. So the modified equation or expression will be Vm sin omega t divided by R minus Vm by omega L cos omega t. Now if we now next draw the phasor diagram of this parallel RL circuit, then that we can do this way. Since V is the reference parameter here, and that is the common value in case of resistor and inductor, so first we will draw the phasor of the voltage. So this is reference, so this will be our voltage phasor. We will draw the phasor of the individual currents. Now since IR here, it is in that expression also we have sin omega t, and in case of voltage also we have sin omega t. So from these two expressions we can say that there is no phase difference between these two parameters. And we also know that in case of resistor, the voltage drop and the current that flows through the resistor, they are in the same phase, so there is no phase difference. So IR will be in the same phase with that applied voltage, so it will be our current phasor that flows through the resistor. So this is IR. Now we know that when we have a pure inductor, then the current that flows through that inductor that lags the applied voltage by 90 degree. That's why in this expression we have minus 90 degree, that value. So now if we draw the phasor of the current which flows through the inductor, then it will be simply, it is only the current which flows through the inductor. So in that case the inductor will be considered as a pure inductor. So here this phasor will be the phasor of IL, and this lags the applied voltage by 90 degree. Now if we want to draw, or if you want to get the net current, the phasor for the net current, then we have to take the resultant of this parallelogram. So this will be the phasor of our net current in that parallel RL circuit. So this will be I that we have obtained here. Now we can see here that there is a phase difference between the applied voltage in that RL circuit and the current that flows. And also here, from here we can see that the current is lagging the applied voltage, but here the phase lag is not 90 degree, rather it is less than 90 degree. So let's assume that the phase difference between that voltage and current is theta. So here I can be now written as Im sin omega t minus theta, since the phase I is lagging voltage and that phase difference we have assumed as theta. So the expression will be Im, definitely it will be sinusoidal, so sin omega t minus theta, and on the right side of the equation we already have these two terms. So the final equation will be like this. Now next what we will do is we will expand this angle omega t minus theta, and from that equation we will be separating the like terms, and next we will be equating the coefficients of the like terms, the way we did in case of series circuits that I have discussed in my previous few lectures. So here again that last line has been written here. Now next is we will be applying again the sin A minus V, the formula of that. So here it will be sin omega t cos theta minus cos omega t sin theta, and on the right side we already had these two terms. Now next we will be separating the equal terms. So here on the left side we have one sin omega t, and on the right side also we have sin omega t. So we are just separating them. So Im sin omega t cos theta will be equal to Vm sin omega t by R. And then next, here we have cos omega t, and also here we have cos omega t. So we will be separating those terms. So it will be minus Im cos omega t sin theta, and from here it will be minus Vm by omega L cos omega t, and minus minus will cancel each other. So now if we equate the coefficients of the like terms, then we will be getting from the first equation Im cos theta will be equal to Vm by R, and from the second equation we will be getting this relationship where Im sin theta will be equal to Vm divided by omega L. Now next what we will do, we will find out the theta value or the phase difference. Now here the values that we have obtained, from here we can write this way, that Im sin omega t, Im sin theta divided by, if we do this division, then on the right side it will be Vm divided by omega L, and here cos theta value is Vm divided by R, so R will go up in the numerator. So finally it will be R divided by omega L. So from here we can write tan theta will be equal to R by divided by omega L, or we can say the phase angle theta will be equal to tan inverse R divided by omega L. Now next we will calculate the maximum value of the total current flown through the parallel RL branch. Now here the maximum current, we have obtained these two expressions, or here these two expressions or these two equations. So from here, now if we take the summation of the square values of both the sides of both the equations, then it will be Im square cos square theta, and from here it will be Im square sin square theta. Now if we add them, then Im square will be the common term on the left side of the equation. So within bracket it will be cos square theta plus sin square theta, which gives us 1. So it will be simply Im square, and from the right side it will be Vm by R square plus Vm divided by omega L square. And directly if we want to find the Im value, the peak value or maximum value total current, then it can be written as square root of that summation of both the square terms. So it has been written directly. Now Vm square is the common term, so when it will come out of the square root, it will be only Vm, and inside that square root it will be 1 by R square value plus 1 by omega L, and that square value of that. Now we know that from Ohm's law, V is equal to I multiplied by, in case of AC circuit it is Z, the impedance of that AC branch or AC circuit. Now if we express I in terms of voltage, then it will be V divided by Z, that means 1 by Z. The reciprocal of impedance we know, that is called admittance. So it is I will be, the current value will be equal to voltage multiplied by the admittance value. So since this is the expression of current, maximum current, so it is the expression of current. So and on the right side of that equation we have voltage, and this term will definitely contribute to the admittance, not impedance here. So now finally it can be written as Im, the peak value of the current, which is equal to the Vm multiplied by this term. So peak value of the voltage multiplied by, we can say, the admittance. So we can conclude here that the admittance of this parallel RL branch, here it is this value. And we know that in case of series branch, be it RL circuit or RC circuit or RLC circuit, we focus on impedance value, and if it is a parallel branch, then we focus on admittance value more compared to impedance. Now the admittance value of that parallel RL branch, that means will be this value, and we know that can be in rectangular form, that can be written like this, G plus JB, where G, we know that since admittance is the reciprocal of the impedance, so G here is the reciprocal of the resistance, because we know, we have already seen that Z is written as R plus J and then the reactance value. So when we are finding the admittance, the reciprocal of impedance, then where it here it will be the reciprocal of resistance, which is called conductance. So that is, we know that is represented by G, and then plus J. B is the susceptance of that AC component. So if it is RL branch, then here it will be X of L, inductive reactance, and here it will be B suffix L, that means inductive susceptance. So that's what has been written here, 1 by R plus, since XL is equal to J omega L, so B, the susceptance value will be 1 by J omega L, 1 divided by J omega L, 1 by R, and we have already seen in our previous lecture that 1 by J is equal to minus J. So here it is minus J in multiplied by 1 by omega L. That means in case of admittance, in case of RL circuit or parallel RL branch or circuit, the admittance, the format of the admittance will be 1 by R minus J and then 1 by multiplied by 1 by omega L. And if we take the polar format of this value, then we know how it is done. That also has been discussed in my previous lectures. And finally, it will give us this value, the real part, the R part we can say, and angle means the theta part will be then tan inverse Y divided by X, we know. So tan inverse Y, here it is minus 1 by omega L divided by 1 by R. So it will be finally tan inverse, and then minus sign will come out of this tan inverse. So it will be minus tan inverse R divided by omega L. So the phase angle, this is the value that we have already seen here, the admittance value, and here the phase angle we have obtained, and the phase angle is minus tan inverse R by omega L. Now we have once said that the phase angle is tan inverse plus R by omega L. Now we are saying it is minus tan inverse R by omega L. This may confuse us a little bit, but the logic is, since here it is admittance and the phase angle is negative. Why? Because when we are getting current value in terms of voltage, so the current, as we have seen here, the current is equal to voltage multiplied by admittance, and voltage we have taken as reference. So the phase angle of the voltage is 0 degree, and we know that in case of RL circuit, current lags and voltage is 0 degree, current lags. So definitely the lagging angle will be coming from this admittance part. So the phase angle of this admittance will be lagging in nature, and that's why here the phase angle is minus tan inverse R by omega L. Now suppose we want to get V is equal to I and multiplied by Z. Now suppose I, if we take as reference, and in terms of that if we want to express voltage, so voltage will lead in case of RL circuit. So that leading angle will come from this Z. In that case, where I has been taken as reference and we want to find voltage, in that case the phase angle of the impedance will be leading in nature. So it will be positive tan inverse that R by omega L. So this phase angle basically is related to or associated with the impedance value, and this phase angle is associated with the admittance value, but both will give us the same value, only difference is the plus and minus, but we have to think that way. So positive, when we are talking about positive phase angle, basically that is associated with impedance in case of parallel RL branch, and when we are talking about negative phase angle, basically the thing that will come in our mind is that phase angle is the phase angle of the admittance. Now next we will find the total instantaneous current. Now total instantaneous current, we have already found the peak value or maximum value of the total current, and it will be again expressed in terms of sinusoidal signal. So I, the instantaneous parameter or instantaneous current, will be written as Im multiplied by sine omega t minus theta. This expression we have already seen in the previous slide. So sine omega t minus theta. Now Vm, and what we can do here, the Im value we have already obtained here. So this value has been written here, means the Im has been replaced by its value that we have obtained here. And then definitely it has a phase angle, and that phase angle will be written or incorporated within this sinusoidal term. So since I is lagging in nature in case of RL circuit, so minus theta, and this angle will be minus tan inverse R by divided by omega L. So this is how is the relationship between voltage and current, and this is what is the instantaneous current, how we express instantaneous current in case of parallel RL branch when we take voltage as reference, and how much is the phase difference between voltage and current. So these things now we have seen in case of parallel branch, and based on this concept or knowledge, we will solve our numerical which will be based on parallel RL branch. Now, as we can see here, again we have a parallel RL circuit which is energized by this AC voltage source, which is sinusoidal in nature, and that instantaneous voltage expression is given as V is equal to 311 sine 100t plus 45 degree. Now here small v, definitely we can understand here it is the instantaneous value of the voltage 311, then that in that case will be the peak value of the voltage 311 volt. And if we want to get the RMS value of that voltage, then that will be 311 divided by root 2. We already know this formula, and if we calculate this, then it will be 220 volt. But here the representation is bit different, and that is here it is omega t plus theta. So omega t, that means omega value from this expression, we can say the omega value is 100, and we know the unit is radian per second. So from the problem statement itself we can take the omega value. Here the no separate linear frequency value is given, directly the angular frequency value is given. But here we have a phase difference of 45 degree. So here voltage, though the expression of voltage is given, but it is not taken as a reference. So it is basically leading by 45 degree angle from the reference, or it has a 45 degree phase angle with the reference. So if we take suppose this as a reference, then the voltage phasor will look like this, or we can draw the voltage phasor like this. So here this is the reference point or reference line, and with respect to that the voltage is leading by 45 degree angle. So this time this will be our the voltage phasor, voltage that we are applying across that parallel branch. Now next what we have to find is instantaneous value of the currents through R and L. Now let's assume that this current is IR and this current is IL. So next we will calculate IR first, and IR we know that will be the peak value of the current, and that will be peak value of the voltage, which is given as 311 divided by R, and R value is 10 ohm. So it is 311 by 10. And next will be the expression of the sine. So it will be sine 100t plus 45 degree. Why it is 100t plus 45 degree? Because the current which flows through the resistor, that is always in phase, same phase with the applied voltage. Since the expression of the applied voltage has this expression, this angle 100t plus 45 degree, that's why the angle for IR will be also 100t plus 45 degree, so that there will be no phase difference between these two angles, or between those two phasors. So now if we calculate this, we will be getting a value of 31 and then sine 100t plus 45 degree, and this will be ampere. Now suppose if we want to, or if we wish to express this this instantaneous current in terms of cosinusoidal, then this can be further written as 31, then in place of sine it will be cos, and cos means if this whole angle if we assume as theta, then it will be 90 degree. This 100 t will be written as 90 degree minus omega t that we have seen, and with that there is a phase lag, so it can be written as 90 degree minus 100 t, then with that there is a phase difference which is 45 degree. But since here we have minus, we are getting minus 100 t, but in our expression in case of voltage which we took as reference, Here the angle is expressed as minus 100t, but in the expression of voltage the angle was omega t. We always express as the omega t as positive. So here what we can do, we know that cos of minus theta, that is equal to cos theta. So what we can do is, this angle we can write as, directly we can write that 100t minus 90 degree. So both are same, and then with that there is a phase difference which is 45 degree. So finally it will be 31 then cos 100 t minus 45 degree ampere, if we really wish to express the current value in the form of cosinusoidal signal. Otherwise sinusoidal is sufficient. Now next we will calculate the current value which flows through the inductor, the instantaneous current value, and that we have already seen that that formula is Vm divided by omega L. So omega value here, it is we have directly getting from the expression of the voltage, and that is 100, and L is 10 millihenry. So it is 10, and millihenry means 10 to the power minus 3. So that will make the inductance value in Henry. That will express the inductance value in Henry. And next is the sinusoidal term. So it is sine, and in case of voltage the angle was 100t plus 45 degree, and in case of pure inductor the current lags voltage by 90 degrees. So with that there will be a phase lag of 90 degrees, so it will be minus 90. So it can be written as 100 into 10, it will be 1000, and here we have again 1 by 1000. So altogether the denominator will be 1. So the Im value here will be 311, and along with we will have the sine term. Here it will be 100t minus 45 degree, and this will be ampere. Now if we want to express this in terms of cosinusoidal, then again it can be write this way, 311, then 100t can be again written as 90 degree minus 100t, can be written as 90 degree minus omega t or 90 degree plus omega t. But since 90 degree minus omega t, again the omega t value will be negative, so we'll choose this expression, this angle 90 degree plus omega t. So here it will be 90 degree plus, in place of omega it is 100t, so 100t minus 45 degree, and it was cosinusoidal, so it will be 311 cos. So finally it will be 311 cos and then 100t plus 45 degree. Now if we complete our phasor diagram for IR in terms of sine, we have obtained this expression, 31 sine 100t plus 45 degree, and this is the phase angle, or this is the angle of the voltage also. So this IR will be aligned in the phase difference between this IR and V will be 0, and they will be in the same phase, in the same direction. So here this is IR. I have kept there is small difference between IR and V, so I will differentiate. Now we know, and IL, the expression is sine 100t minus 45 degree. Now this minus 45 degree is basically with respect to the reference line. So this is our reference line. So with that it will lag, this IL will lag by minus 45 degree angle. So and value wise, the value of IL is almost 10 times of IR. But in phasor diagram I cannot accommodate, so just roughly this is IL. So this will be the phasor of IL, and this will be the resultant of this parallelogram. That means this is the phasor of our net current or total current, which is I. Now this is our reference, and we have seen here that the voltage, applied voltage with the reference has phase angle, the phase difference is 45 degree, and voltage is leading that reference, so it is 45 degree. And also in case of IR we have seen that the phase angle if we consider the sinusoidal, then phase difference of that IR is 45 degree with the reference, and that's why we here the phase difference between this reference line and IR is also 45 degree, and as per logic we know the applied voltage and the current that flows through resistor, they are also in the same phase, so that logic also satisfies here. And from the expression of IL here, as we have seen that it is 100 t minus 45 degree, and this phase difference is basically with the reference line. So here this, if we take as 45 degree this angle, so here this IL is lagging this reference line by 45 degree, and when we took this resultant of the net current, so I, as we can see here, is also lagging the reference point, and that angle is suppose theta 1, that can be taken as theta 1. And also we can see here that the phase difference between the applied voltage and the current that flows through inductor is also 45 degree plus 45 degree, that is 90 degree. So that logic is also satisfied here, and this is the phase difference between the reference line and the net current. And if we want to know that what is the phase difference between the applied voltage and net current, then that phase angle theta will be theta 1 plus 45 degree. And here also we can see that the current is lagging the applied voltage, and since this is a RL circuit, so current will lag applied voltage, and that phase difference or the lagging phase angle will be theta 1 plus 45 degree. Now as per the question, the next requirement is to find out the RMS value of the total current. Now what we will do next is we will find the RMS value of the resistance, and that will be the peak value, which is 31 divided by root 2. We know that is the peak value divided by root 2 is our RMS value, this much ampere. And IL, the RMS value of the inductive current or current that flows through inductor, that will be 311 divided by root 2. And if we want to know the RMS value of the total current, then it will be IR square plus IL square, and then directly we are finding out the value of the net current, so it will be square root. So it will be 31 divided by root 2, then square value of that, and then 311 divided by root 2, then square value of that, and then square root of that summation of the square values. So if we calculate further, then it will give us a value which is nearly equal to 221 ampere. Now this is the value, RMS value of the total current, but along with the value, if we want to know the phase angle means theta 1 between this current and this reference point or reference line, or if we want to know the phase difference between this net current or total current and the applied voltage, then for that we can calculate the RMS value of the total current in other way, and that will be, we have to consider the phase angle also. So in that case, IR can be calculated like 31 by root 2, and we have to consider the phase difference. And in case of IR, the phase difference was 45 degrees, so we have considered that value. And in case of IL, it was minus 45 degree, so it will be 311 divided by root 2, and then that angle will be minus 45 degree. So next, if we calculate the RMS value of the total current, then it will be 31 by root 2 and then angle theta, so it will be written as cos theta plus j sin theta, so it will be cos 45 degree plus j sin 45 degree. And then IL part, so IL is 311 by root 2, and it will be written as cos of minus 45 degree, which is cos of minus theta is equal to cos theta, so it will be cos 45 degree plus j sin of minus 45 degree, so it will be, I am writing directly, minus j sin 45 degree. So it is calculated this way, or it can be, so 31 by root 2 and inside, and if we export the values of this cos 45 and sin 45, then we know both the values are 1 by root 2, so it will be 1 by root 2 plus j 1 by root 2, and in the second part it will be 311 by root 2, and cos 45 is again 1 by root 2 minus j sin 45 is again root 2. If we simplify further, then it will be 31 by root 2 and multiplied by 1 by root 2. That means it will be 31 by 2 plus j, again 31 by 2, plus it will be 311 by 2 minus j 311 by 2. So if we separate the real and imaginary part, then it will be 15.5, and from here it will be 155.5. So it will be 155.5. I am adding the real terms separately and imaginary terms separately. So it will be j, then 15.5 minus 155.5. So it will come as this will be 171, and this will be negative, so minus j, and it will be 140. Now this is expressed, the RMS value of the total current now is expressed in terms of rectangular form or in rectangular form. Now to get the phase angle, we have to convert this into its equivalent polar form. So either we can use calculator, or we can use the formula that I have already discussed in one of my previous classes. Whatever way we apply, then finally it will come as 221, and angle will come, the angle value will get as minus 39.31 degree, and since this is current, so unit will be ampere. That means the RMS value of the total current will be 221, that we have already obtained in our first approach, and this time the phase angle is minus 39.31 degree, and this phase angle, this phase difference is basically the phase difference between I and this reference line. So this theta 1 is minus 39.31, and if we want to get the phase difference between the total current and applied voltage, then it will be minus 39.41 degree, which is theta 1, and again the V is already phase lagged by 45 degree, so it will be minus 45. So finally it will be, so the phase difference will be minus 84.41 degree. So we can say either the current is lagged by minus 84.41 degree from applied voltage V, or we can say the applied voltage leads the total current by 80 plus 84.41 degree. So this was the whole explanation of parallel RL circuit. Thank you.